Alright, hello everyone. Um, Today we will be starting ML1, which goes into more of the implementation of machine learning algorithms that we talked about last week. I'm going to start here in about, I don't know, 1 to 2 minutes, but I want to give everyone a chance to sign in. The link in the description. And if you want, you can clone or download this repo or this like notebook basically off of our GitHub. If you go to our GitHub, which is, one second, let me find it. Uh, Oops. If you see at the very top here, sorry, it was hidden. If you go to GitHub/DSIUFL, you can see all of our repositories, all of our notebooks. And if you go to machine learning one, ML1, you'll find it. So if you want to follow along, that's definitely recommended. Or you can just, watch me code as well. Additionally, please ask questions in the chat. If you want me to clarify something, if you have maybe like an extension to something I'm saying, definitely like chat interaction when I'm doing these. And then, yeah, so I'll probably give 1 or 2 minutes to make sure everyone gets in. Um, but I will, yeah, and also please sign in. So I'll get 1 or 2 minutes and then we'll get started. All right, so let's go ahead and get started. No reason to keep waiting. So today we'll be going over kind of implementation, like kind of a simplified notebook of how to start the data set, how to kind of like, do introductory data analysis, kind of clean your data, and then eventually, put it into a machine learning algorithm and get the results out. So yeah, so today we will be using this Pokemon CSV, and I think if you remember last week we talked about we could use this data set to try to determine binary classification of whether a Pokemon is or is not legendary based on its um, like characteristics or like statistics. So things like attack, defense, speed, those kind of things. And so today our goal was to first import data set, and then it's going to be to try to find an algorithm that will most accurately predict whether a Pokemon is legendary or not based purely off its statistics. Um, yeah, so make sure there's no questions, and we'll get started. Looks good. So I'm going to get started. And if you have questions along, let me know. Or if you want me to slow down, please let me know as well. So the first thing we're going to do here is import our usual library. So this is pandas and as PD, and then import numpy as np, whoop, numpy, and then we want to import a data set. So this will be so this will be Pokemon. Let's call it Pokemon equals PD dot read underscore CSV, and this will read it as this is just simply named Pokemon dot CSV. And then we'll just do Pokemon dot head, which basically takes the first 5 rows and just displays it. And then before we start, I need attach interpreter. So we should be good to go. All right, so we see here we have a data set import in where we have the Pokemon number, which I think this is related to like the Pokedex, if you're familiar with Pokemon, name, type, all that kind of stuff. Um, Definitely some of it's gonna be more useful than others. So the first thing I'm gonna note here is that I probably don't need, or I know I don't need the name, because if we can't use the name because we can't map the name to a numeric number, and we probably don't need the Pokemon's like Poke ID. So our first thing we're gonna do is remove it. So what we do is Pokemon. So we're basically just assign the variable back to itself with their moved values or columns. Pokemon dot drop, and then the first thing you do is you pass in the columns you want to drop. So name, and then number, and then you will say axis equals 1, and that means that you're going to drop a column. If you do axis equals 0, that'd be a row. Say it again. Dot head, just to make sure we did it right. And there we go. So now we have basically just removed the first two columns of the Pokey ID and then the name, since those aren't really useful for our analysis, and because we can't really translate those. Because technically this is a number, but the number isn't correlated to anything like legendary or not, so it'd be kind of useless. Since this, Pokemons are randomly assigned a number, so really no point in the name you can't map to like a value. So yeah. So basically, say the first column is not needed, so we'll remove it. And then we can just kind of show, yeah. So first thing we can do is we can kind of show like one of them. So we have all these. We can just do sample. Also show one of the columns or rows. Sorry. So this Pokemon has normal, flying, all that kind of stuff. One thing I'm trying to show here is that here we can do this. Describe. So if you see here, is that or let's say is NA, or is NA maybe. Yeah, so the problem is that there are some columns, I guess, okay, so here's one thing that I'm trying to show you is that, dot, basically what I'm trying to show you here is that the second type is not always guaranteed to be there. For example, it can be NaN, for example, right here. I guess I didn't need to do all this, but let's just sample again just for it. Okay, here you go. One thing you have to realize here is that, Pokemon could theoretically only have, or could only have, one type. It doesn't have to have two. So we have to, take care of this NaN value, and we're going to do it in a couple different ways. What we'll probably end up doing here is we're going to map a type to a number and change, since it's like not a continuous number, a discrete number, or since it's not continuous, we're going to map this word into a discrete number. So basically, like grass might be 1, fire might be 2, and so on and so forth. And yeah, so luckily this dataset's pretty pre-processed for us. We don't have to do much here. For example, we don't have to worry that much about null values, for example, in type 2. We don't have to worry about redundancy, for example, if there's two Pokemon or the same Pokemon in here twice, things like that. Traditionally, this kind of step of cleaning our data would probably take the most time, but luckily, we purposely chose a dataset that's pretty clean just so that we don't have to waste too much time on that. Next thing we'll have to do, okay, so now that we have our data kind of in a good spot, it's clean, now we have to basically see what variables would be most helpful in determining legendaries. So if you think of this as a function where you're mapping the input, which are these columns, into the output, which is legendary. So basically think of there's some kind of function using these variables that we can then predict the outcome. So a good way to see this would be to basically compare scatter plots, right? Or not scatter plots, a box plot, right? So you can see I guess best way to describe it is let me show you, I guess, and we can talk from there. So up here, this is called a set plot, which basically does all of our matplotlibs up for us. So we don't have to worry too much about it today. If you want more explanation, you should go check out the Python visualization class or workshop that I did, I think 2 weeks ago. That'll give you a better understanding. But if we, and I'm just copying and pasting here, use Seaborn, and we run this, whoops, we can see here is that HP, for example, were a false. This line here is all the Pokemon who are not legendary, and then true is where all the Pokemon who are legendary. You can see that there is, on average, a difference of HPs. So if you're trying to use HP to do a difference between the two, you might get some good results. And we can basically copy and paste this a bunch of times through all the different attributes, and we'll show here. So now this is copy pasted directly from, I don't want to type it out by hand, but basically what we do here is that we call Boxplot, where you can see here the distributions is shown along the spline, and where X is our legendary, which is true or false, or Y is our variable here, and then data is the data frame Pokemon. Our palette is like basically our colors, which we set, which is like something you set, and then X is like basically which of these boxes we put in, since I think up here we set the number of subplots. Yep. So yeah, basically, okay, so let me explain what this does. So basically you can see here, for example, that on average, the legendary Pokemon have more attack than non-legendary. So for example, if you were, an algorithm and you're trying to determine whether a Pokemon is legendary or not, you could say, okay, is the attack, for example, on average, or is attack high? And if it is, you can say, okay, there's a higher probability it's going to be legendary. And you can kind of do it for each of these. And you can see, for example, special defense, if it's higher on average, it's more likely to be legendary. But for example, on HP, there's really not that much of a difference. If you look here, even though it looks like it's a little bit higher, I think it's on like maybe 40 higher, it's really not that big. So this would probably give you a less of a probably boost your probability, which not necessarily how the algorithms do it, but you can kind of think of it in that way. So ideally, you want the maximum separation between the middle of these two box plots. So for example, if you had one down here and one up here, that it'd be really great, because if it'd be a really good way to separate the variables. And for example, if you had ones that were almost identical, you probably don't want to include that in your model because it would just be very confusing. And yeah, so it's like one way you can do feature selection. Feature selection is a whole other topic, but basically when you're first starting, you want to make sure that whenever features, or features can has some explainability, which meaning that there's some difference between your two classes of your output. Yeah, as you can see above, there are clear distinctions in the rank relate to other features. Basically, it's just saying that from the two outputs, legendary or not, there are differences in each of the attributes. So that's kind of a really fast forwarded version of bringing your data, cleaning it, and exploratory data analysis. These will usually take a lot longer. Obviously, box plots are just one thing you can do. You can also look at scatter plots, look at correlations between legendary, or between different things, and see if things are correlated. You could do all kinds of things. You could also do different kinds of feature selection, or like transformations. You could do things like normalizing the inputs, or standardizing, or principal component analysis, all kinds of things you can do. But we're just trying to keep it simple, just to focus on the machine learning today. So if you have questions, let me know. Definitely talk about it, but I'm going to start moving forward with the actual objective. So the goal of this workshop is to come up with the most efficient model to predict the rank. Whoa, 1 second. I think this is outdated. 1 second, let me read it. Yeah, so this is outdated, so don't read this. Basically, our goal for don't read this is all outdated. This used to be older. But basically, our goal of this project, or goal of this notebook, is to be able to say, like I said before, if we're given inputs, how would we determine the output, which is our legendary or not? So basically, if we don't know the name of Pokemon, but we're just given its like types and HPs and all that kind of stuff, how would we then know if it's legendary or not, or how could we guess basically most accurately? So the first thing we need to do is we need to convert the types into numbers. Basically, we're going to map, for example, grass could be 1, fire could be 2, so on and so forth. This is also called, categorical analysis. This is called like creating dummy variables, or there's all kinds of things, so like one-hot encoding, integer encoding. I think one-hot encoding is probably the most popular right now, but we will do just integer encoding. So basically the idea is that we first want to get all the unique types. So let's get the Poke types, which is just going to be a list. Okay, let's do this. So the first thing we should think about is how to get the unique types of the type 1, right? So if we do Pokemon dot, and you get the type 1, and you do dot unique, you get you get some of the types, right? And the thing is that you don't know is if all the types, if type 1 is representative of all the types or not, because there could be, for example, summon, for example, type 2 that are non-type 1 and vice versa, right? So ideally you want to join these together. Okay, for example, nan, right? Exactly. Try to find another one. Anyways, so you want to kind of combine these together without duplicates. So a great way to do that is if you're familiar with sets, where a set is an unordered collection of objects that without repeats. What you can do is you can union these two. So if you do this, oops, and then you union, oops, I did that wrong. Okay, I have to do set dot union. All you do is you just get all the unique types of both things, and that there's no repeats, and so basically allows you to do everything. But unfortunately, this is a set, and all to do, you want to change it to list, all you do is you just cast it to list. And that's basically the easiest way to get all the ones in type 1 and type 2 without repeats. And then we'll also assign this a variable called type underscore Pokemon. And that's the easy way to do it. So that's all our types of Pokemons. And now we want to be able to basically map one from a Pokemon's name to a Pokemon number, or like a number basically. So a good way to do that is a dictionary, where basically our Pokemon names are going to be our keys, and the value or the output of it is going to be the associated number. So we can do that with a type, we'll call it type underscore dict, or we have a dict, whoop, of zip. We're basically going to combine the two things where we have the type of a Pokemon's, then we'll have range of which is basically just which is it basically starts at 0 and ends with the number you do, or 1 minus a number, and we'll do the length of the type Pokemon. So if I can show you this, for example, dict. So if nan's 1, nan is 0, bug is 1, water is 2, and so on and so forth. Yeah, and so basically we're going to now map it. So what we can do is we can take our data frame. So we'll call it Pokemon, and we'll just call this type, I guess. Or sorry, we'll reassign one. We'll reassign it. So Pokemon type 1 equals Pokemon type 1, and then what we're going to do is apply a function to it that will use our dictionary. So we'll use a lambda, which basically lambda is like a small function that you don't declare, but it's just used inside of it, where all you do is you take the type dict of x. Right? And so we can just do that twice, one for type 1, one for type 2. And now if we go and see our data frame again, Pokemon.head, we can see now that they're all changed. So now the computer can understand these numeric values. And yeah, that's kind of what we did there. I'm going to stop here for a second, drink water, and let me know if you have any questions. Alright, so now that our stuff is like, all numeric, besides our output, which will soon change to be 1 or 0, now we will basically create our features, which is basically just splitting our data frame, I think, into like data frame into features and targets. So our features is simply Pokemon and then we're going to drop the legendary. Whoops. And then we're going to access 1 since it's a column. And then we can do feature dot head, or we can do sample, doesn't matter. And we'll do a sample of 3. Whoops, features. And there you go. So it's a random sample, which basically the head takes the first however many, and sample takes a random sample. And then we'll get our labels. So we'll call I guess we'll call it labels, or targets, the same thing. So it's Pokemon legendary, and then we will do the head of this as well. So labels. So this is just a single column, right? With it's true or false. Also, one thing we're gonna have to do probably in the future is we're gonna have to, since this is a Boolean, we want this to be a 1 or 0 and not true or false. So all we can do, I think, is do this. Nope. Sorry, there, my headphones died. I think you just do dot as type ints, maybe. There you go. So as you can see, if you as type, basically you convert it from a Boolean into an int, and we'll just for like memory's sake, we'll do it as a small int since it's only 0, 1, which 8 indicates how many I think bits you use. Anyway, so now that we have our stuff, basically we have a features variable, which is all of our inputs, and our labels, which is our outputs, where all of our inputs are numbers, and the same thing with outputs. We can now start. So the first thing is really important about machine learning is having a training set and testing set. And the reason why is the training set will allow you to basically train your model on the relationship that it has to create. But as we talked about last time, we have to worry about overfitting, which is the idea that it learns your data and not the relationship. And so the test set will allow us to identify overfitting. So if our testing accuracy or any type of metric is significantly lower than our training, it's a good indication that it overfit. So yeah, so there's a really easy way to do it using sklearn, which is another package. So if we say from sklearn dot what's the exact one? I believe it is model selection, import train test split, and then we'll say is we'll do x underscore train, y underscore train, x underscore test, y underscore test equals train test split. And then we'll call this features labels, and then we'll make the test size, or sorry, the test size, let's say 20%. So basically 20% of our data will be in the testing set, and the rest will be in the training. So as you can see here, whoops, I did that backwards. Yeah, sorry, it should be x train, y train, x test. Sorry. Yeah, so there you go. Whoopsie. There you go. So we have our training set, which is 640, and our testing set, which is 160. So yeah, so now our variables are in a nice set. So we'll first use our x-train and y-train variables to train our models, and then we'll use our x-test to basically see the performance and make sure it's not overfitting. So like we recommended last time, the easiest way to find the best model is to basically test them all. So basically train each one and see the accuracy or whatever metric you're going to be using. So we will first start with our KNearest Neighbors, which is probably one of the most flexible models, but most of the time you need a lot of data and it's very has a high variance but low bias. So basically, yeah, so let's go ahead and import it. So we say import or from sklearn.trees, I think it is. Import k nearest, maybe it's trees. Import k, let me see. Oh, sorry, not trees. We're not doing, sorry, neighbors. We're doing KNearest Neighbors. Import k and then classifier. And so we use classifier instead of the aggressor because we're having a binary output, which means it's like 1 or 0. Remember, classification is for discrete outputs. So basically, 1, 2, 3, 4, 5, while continuous or regressors are used for things like, predicting the price of a house, where it can be like 13,010 cents or whatever. It's continuous versus discrete. So now that we import it, now we can initialize our classifier. So let's just call it KNN, which equals KNN classifier. So we first create the model, and then to train it, it's actually really nice. You do just knn.fit, where you feed in your x and y, but we're just going to do the training. And then to evaluate it, we will just use a score method, I believe. Yep, so we'll do print, and then we'll call this a training score. And then we will put knn.score. And let's call it x. We put in our x and y again. X train, y underscore train. And then we can just copy and paste this, but then repeat, but with testing. And this will maybe allow us to see our accuracy, or like how good our model is doing, but also let us identify if there's overfitting going on. So here we go. So you can see here that the KNN had an accuracy of really high, of almost 98%, and the testing was at 95. So really not, doesn't seem like there's overfitting going on. What is that? 3% is not that much. We really expect overfitting to be a lot higher, like 10 up, kind of is where you start thinking about it, depending on your data set. But also there's things we can change here, right? So last time we talked about hyperparameters, basically things that we can alter in the algorithm that will allow us to get better or worse results. And for KNN, the thing was the neighbors, basically how many of the neighbors does it look around and try to find a result. So what we can do is we can say, okay, let's look at the parameters that we can change. And you can see here, so this algorithm, we don't really touch that. That's something that's kind of beyond this. Basically, it's how it like sets up the data structure behind it. The leaf size, yet again, it's thing in the back end, it's how it's structured. The metric is basically how it determines the difference between how far away your points are from each other. Electric parameter, don't worry about that one. And job is basically how many cores on your processor you use. So, for example, if you're doing a really big job, you might want to set to be, for example, you have a 4-core processor, you want to set to 4. -1 is all of them. So if you just want to compute and kind of sacrifice some of your other PC's computing power. But the one we're really interested here is the end neighbors, which is basically how many points does it look around when it's evaluating. And right now it's currently 5, but what if we change it? So for example, let's vary this from, like, let's say starting at 1, let's go up to like 15 for example, and let's see how well it performs. Yeah. So okay, so let's first thing we're going to do is going to say for, let's say neighbors in range, let's say 15. So we're going to get from 0 to 15, where neighbors going to be starting at 0 and iterate each time up to 15. First thing we'll do is we'll call it a model, and we'll fit it. And you can do this as well. This is what I do most of the time. So you can kind of combine the first and second step. And then what you'll do is that you'll score it. Oop, model.score x underscore test, y underscore test. Whoops, sorry. And then we have to alter, see it's all the same here, so I messed up. We have to do is we have to alter the number of neighbors you use. So what you do is you do, look up here, and neighbors equals neighbors. Let's try it now. Oops, sorry. So the problem is it's crying me because range starts at 0. Let's start at 1. What is it doing now? Okay, let's do high numbers to see. Okay, so it does vary slightly. Let's store it in a variable and let's plot it on a graph, I guess would probably be a good way to do it. So let's call it accuracy list. And instead of printing it, let's append it back to this list and then we'll display it. So accuracy underscore list dot append. And then so that will contain basically all the accuracies. And then what we can do is that using, I think the same, we'll use the same thing from up here. So set plot, and we'll, whoops, go down a little bit. I'll just copy and paste this for time's sake. We're doing instead an 8x5 plot, which is basically the size of it, and then we're going to have a line plot where x is how many neighbors we're going to use it, and our y is our accuracy list. And let me change this to 41 so it's the same. As you can see here, there's our accuracy varies depending on the number of neighbors we use, and ideally we probably want to use the best one. So if you look here, you probably want to say maybe somewhere from 6 to 8 maybe. I don't know what that is, maybe 6 to 7 would probably be our best one. So if you're doing this and you're trying to get the best score, you'd probably want to use that kind of model. So we can kind of recreate this by basically saying create a final model equals k and then classifier where n underscore neighbors equal, let's say 6 will fit x underscore train y underscore train, and then we'll show the accuracy. So kn underscore final dot score x underscore test y underscore test. So you can see here you get that higher accuracy. So that's like one way you can like optimize your machine learning algorithms by kind of varying it, which is also, this is like a more basic version of a grid search, which we'll talk about later. Any questions? And otherwise I'm going to move on in a minute. Feel free to ask chat if you have anything at all. But yeah, so basically we could also do this, for example, with P as well. So if you want to do P, you could change that as well. So you can create a double for loop and maybe show some type of like three-dimensional plot where on X you have your neighbors, Y you have your P, for example, which is like, and then which is like, this is really like what type of norm you're doing. So for example, this is where I use L2 norm, which is like, square root of x squared plus y squared. But you could do like L1 norm, whatever norm, you could change that where your y is your norm number and your z, which is your accuracy. So you can kind of see like a plane where you can ideally where the best parameters are. But we can also use this function grid search that we'll talk about later to do this all for us. But yeah, so now we will keep moving forward. Alright, so another thing we can do is we can show the predictions. So not only can we score it, we can also predict. So we can do kn final.predict. And we can just do, for example, x test. And this will show us basically where it thinks legendaries are and are not, which is definitely important sometimes. Alright, so let's move on to random forest. So random forest was another type of model where basically it was a not very accurate. Sorry, this is old stuff too. I'm looking at 77.5, but we had much higher than that. Let's see if random forests are. Ideally, we'd want an accuracy one basically always predicts correctly. So yet again, let's import it. So we say from sklearn.ensemble import random forest classifier. Use classifier again because um, we are doing a regression or we're doing classification, not regression, since our outputs are discrete. So first, we're going to initialize the model. So we can say a forest equals random forest classifier. We're going to use a Gini index to measure the feature importance. So yeah, so basically if you guys remember from last week, we talked about how the model decides to split basically our features and upon where, and Gini is one of them. So here, let's do this. So if we do forest dot get params, we can see that. So these are all the different types of parameters we have, right? And criterion Gini is one way to split our features. If you want to learn more about that, look up random forest splitting criteria. There's things like entropy, all that kind of stuff, but we're not going to worry too much about that. All we're going to worry about is a number of estimators, I think, for this one. Yeah, so it's already using Gini by default, so you can see here. And then it's using 100 estimators. Let's push this back down to 10, because we don't want to take it forever. And let's now train the model. So forest.train x underscore train y underscore train. Oops. And then let's see the accuracy. So we'll do forest.score x underscore train y underscore train. And then we will print this. X underscore test, Y underscore test. Whoops. What happened here? Oh, not train fit. Aha. So here, example of in the training, it got perfect accuracy. It never got wrong. But in the testing, it got worse. So this is an example of usually when you give 100% accuracy, there's usually an example of overfitting happening. I'm not too worried about it, considering it's only 8% or like 7.5% less. But usually 100% accuracy is not a good sign. But let's try to tune the parameters, get maybe a little higher of a test accuracy. So in this example, we're going to tune the n estimators, which I set at 10, which is basically how many decision trees it creates inside the random forest. And there's other features such as the criterion. So for example, we use Gini, whether you bootstrap or not, the number of features. But we're just going to accept the default ones besides the n estimator. So let's yet again basically copy and paste what we did above. Let's just take this code. But instead of doing KNearest Neighbors, we're going to do random forest classifier. Instead of neighbors, this is going to be n underscore estimators. And this will not be neighbors either. We don't need to change this. We can just change this to I. It doesn't really matter. But now we're going to, so let's go to, so yeah, we're going to basically change the number estimators. Let's go to 50. And say it takes a minute. And why is it breaking? Because I didn't change this. Okay, so here you see this is an example of, this is why random forests are really high variance. Depending on the number of estimators we do, you see the accuracy changes quite a bit. And yeah, so looking at here, it looks like the best model would be, as you see kind of there's a trend here, the more estimators you have, the better, which makes sense. But maybe let's choose the one, I don't know, let's choose the one at 49, because it looks like it's really high. So we can just call it, final underscore forest, where it's a random forest classifier, array fit, x train, y train, and then we can score it. So we can do a final underscore forest dot score x underscore test, y underscore test. So maybe it's not it. So maybe it's, oops. Reason why it didn't go very low is because you see it is at 10. So we got that. Or no, we need to change the n estimators. So n estimators, let's say 49. Okay, so yeah, so this is actually a little more complicated than it just. Okay, so the reason why is that there's some random aspect to random forest, as the name suggests. So what we can do is that we can kind of make this stagnant by doing the random, basically setting the random state, and you can get a difference. So, if you ran this 100 times, you get different results. But if you set the random state, if you run again, for example, you're gonna get the same result. So now I can say, okay, the best one appears to be something at was that 38? Let's see if I can. Oh, 38. No, 37 maybe. No. Oh, because you know why? I didn't do the random state. 365. This should be 38, I think. There you go. So that's your answer. So yeah, random states are really good for repeatability. So it lets you basically to stagnate random parts of your model. Don't vary random states. So I think it might be tempting to say, okay, if I change a random state, I can find one with the highest like accuracy in the test set, which I mean logically would make sense, but if you think about it, is that what you're doing is you're just trying to overfit your model to get the best results, when in reality you want your model to be getting the underlying relationship. So doing that wouldn't really help you, and if anything, it might hurt you a little more. And in reality, you're probably not going to get, if you shouldn't be getting that big of a difference depending on your random state. So yeah, that's kind of random forest in a nutshell. Yeah, so since creating the model, it's randomized, not like KNN. There will be difference in testing accuracy each time because different bootstraps, or whatever. And you can basically tell this by using the random state by setting it. So if you can see here, our random forest got 95.6. Let's see, and then our KNN got about the same actually. Is it exactly the same? Oh my god, it's exactly the same actually. So you see these two are about the same, which is pretty surprising actually. I would expect the random forest to do better, and we can kind of talk about that because usually usually cannons would do worse because of a small data set. And usually cannons are very hungry for data. It requires a lot of data for it to be dense and perform well. But apparently in this situation it does pretty decently. So yeah, let's move forward to support vector machines. And I'll stop for a second, get a drink of water, and let me see if any questions. Alright, so let's do support vector machines. This is another type of classification model. The way we're going to do it is the same kind of thing. At this point, you should kind of know what's coming up. We're going to import it, so from sklearn dot, I think it's a svm, import svc, which is support vector classifier. Or we're going to initialize it, so svc equals svc. We're going to train it, so svc dot fit. And then we're going to test it. So let's do it. So svc dot store underscore train, y underscore train, print svc.score, x underscore test, y underscore test. Alright, so here we can see that there's really no overfitting going on, but we have a much lower accuracy on both the testing and the training set. But hopefully we can maybe boost up the scores using, or basically tuning hyperparameters to gain the best result. So if we look at our hyperparameters, which we can do by the get parameters, so svc.get params, you see there's a lot of different things we can go on here. So the kernel, for example, RBF, for example, the C, which is a hardness, basically we talked about last time, it's a regularization, how important is that all the points are on the same side of the line. Random state, or random state's not important. Gamma, which there are all the things that we can basically adjust. And I think, yeah, so we'll get the optimal C and gamma parameters, which are both numeric. Yeah, let me see how they do it first before I move on. So now we're going to use a grid search. So grid search is really important for when you are tuning one or more parameter at a time. So when you're doing, or sorry, more than one parameter at a time. So when you're doing one parameter at a time, you can easily do this method, which is more than valid. But say you're tuning like 15 parameters, or all these at the same time, it wouldn't be very ideal to do them one at a time because, for example, if you change C, it might affect the other ones as well since they're not independent. So what you can do is you can basically create a like a grid of parameters that you want to test, and it'll test all the different combinations of them, and then give you and then it can return the best one. So what we'll do is create SVC params, which is just going to be a dictionary of our different params we want to test. So let's, for example, vary C. And C is going to be between 0 and 1. So let's do np.line space 0, 1, and let's do increments of like say 10 or 0.1. Let's do the same thing with gamma. Make sure I'm doing the same way they are in a second. Okay, they don't do exactly this way. What they do is they do this. I'll do one their way and one my way. 0.0 or 0.1. Then I do 0.01, 0.001. So you can do either way. This way is a little more like just like introductory. What you do is you maybe would run this once and then you find which one's the best and you maybe try to hone in on the best parameters slowly. Either way works. But now what we can do is we can initialize our grid search. Sorry. So yeah, so let's since we're varying C and gamma, where C can be 0 or 0.1, 0.01, or 0.001, and our line space can be any value between 0 and 1 in increments of 10. What we can do is we can first import grid search. So from sklearn.model selection import grid search CV, which is cross validation. We're going to check each combination of our grid values, and then it's going to give us the best result. So we're going to first initialize, so let's call this svc underscore grid equals grid search CV. And what we have to do is we first have to import our estimator, or not import, but give estimator as a parameter. So we'll call this svc. And then we have to give it the parameter grid, so svc underscore params. And now what we will do is we will, fit, which basically tests all the different combinations. So svc underscore grid dot fit x underscore train y underscore train, and then we can print the best score, which is, or the best parameters, I guess. So I'll just copy and paste this for time's sake. But basically, it'll print our best parameters. SEC parameter is not defined. Oh, you know what? It wants this. Doesn't want equals, it wants that. Uh, okay, let's just do their way, I guess. 0.01. You have to do some casting, which I don't want to deal with right now, so let's do it simpler way. And I messed up. Oops, they called something different. SVC underscore grid. Alright, so as we can see here, is that our best parameter was C at 0.1 and then gamma at 0.1. So that one should be our best. So what we can do now is we can say our SVC final. So SVC underscore final. What we can do is really easy. Just take your SVC grid and extract the best model. Best estimator, and that basically pulls out the best model that fit, which is the one given above, and then we can score it now. So SVC underscore final dot score x underscore test y underscore test. Alrighty, that. Alright, and that's our answer, right? So you can see SVC performs a little worse. Obviously, we can tune it. Sorry, we could tune this even more to get better results, but let's just move on. You could keep adding different parameters in here. For example, you could change the coefficients or any of that kind of stuff, or keep altering the C. For example, you could add 0.5 and keep going along that and try and find it. Usually the way you can know to stop when to use or stop using these different where we found the best hyperparameter is when if you have, like, for example, a set like this and your hyperparameter is in the center and not on the edge. So what this is telling me is that ideally it wants a higher C. So if you did 0.0, I don't know, 1.5 and it still came back at 0.01, it's probably good. But if you keep getting on an edge, you should keep adding values, oops, that are on the edge, so we can try to get in the center. And that'll let you kind of know when to stop. And you can use this in any kind of classical. So you can use this with a random forest, you can use this with linear regression that we talked about last time, or the KNN, for example. Yeah. So last one we want to do is we want to use a multilayer perceptron. So this is an example of our neural network. When we start getting deep learning, and these are a little more complex. But if you think about it, let's think about it, right? So first, I think design of a multilayer perceptron or our neural network. So first, you think about our input layer, which is the number of features we are training on. Right? Which is basically, if you go up to our features column, if I can find it, it's just going to be all these, right? So if it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we're going to have 10 inputs, right? And our output is going to be just a singular column, right? So it's just going to be a 1. So if you go back down, this is wrong again because it's for old thing, but imagine input layer is 10 dimensional and our outputs can be 1 dimensional. And then the hidden layer is what we can determine. So this can be as large as we want. It can be, there can be multiple of these in the center, but we can change that ourselves. So first we'll import from TensorFlow. So I think it's just now this. Hopefully, otherwise I have to restart my kernel. Okay, one sec. Let me change my kernel because I don't think this kernel has TensorFlow currently on it. So run all these. Hopefully this will work. Okay. Oh, one sec. Something's happening here. Let me restart and run everything again. Sorry, this package was not initially installed on that kernel, so I have to restart and get a different one. It's not running? It is running. Okay, so now, okay, so we have imported, sorry for that. What we first thing we're going to do is we're going to encode the labels. So for one-hot encoding, what we kind of did already. Sorry, so let me just import this in and explain. I think it's a lot better than me just typing it out. So we first import a label encoder and one-hot encoder. So a label encoder is basically allows you to take our types and then automatically um, like turn to a number. Fortunately, we already did that for our Y train and Y test lots more simply. So we can basically ignore this because this is already done. Um, but yeah, and if you want to do one-hot coding, so this is the code for it. I don't want to go too much into it because we've already done this. But basically, for example, if we had one-hot coding, we'd have where the first column would be for legendary, second column would be for not legendary. So if you had a legendary, it would be 1, 0, and for non-legendary, it would be 0, 1. Either one works. It's usually one-hot coding is for one that has multiple outputs. Say, for example, if you're trying, or if you have a picture of numbers 1 through 9 or 0 through 9, you will have 10 outputs. So this would be good use for one-hot coding. But when it is just 1 or 0 binary classification, we can just simply transform the true or false into 1s or 0s, and that's enough. But we'll run this as well. Maybe not. Why is it complaining about sklearn? Oh, it's not like all the package is conflicting now. Okay, so we're not going to do this. We already know this. We don't need to do this. Hopefully you won't run into any more problems. But basically, sklearn is installed in this package. It's a TensorFlow package or TensorFlow interpreter. But yeah, we're not. It's already did this by basically casting it to 1 or 0 earlier. So now let's initialize MLP. So the way you do that is you do NN, we'll call neural network, is equal to a sequential, which is basically the idea that numbers go in sequentially or the data flows in sequentially. There's such things as recurrent neural networks or convolutional and have different kind of flow. But we're using sequential. Next thing we want to do is we want to add some layers. So we'll do nn.add and we'll create a dense layer. We want the dense layer, this will be our input layer, right? So we talked about this before, is we want to be a size of 10. And then we need to also talk about the activation function, which is, if you remember from last time, this is basically our like nonlinear function that will allow us to allow it to converge faster, or basically allows us to become a neural network. So for activation function, we're going to choose ReLU, because that's ReLU, which is rectified linear unit. That's kind of a standard one to use. And then, oh sorry, what you need to do here is not, this is not, sorry. And then we'll add our input. So this is the first time we have to add an input function. Input dimension equals length of x underscore train dot columns. So okay, so this is actually the first hidden layer. So this can be, for example, 6. This is our activation function, and this is our input layer. And then we can keep adding layers if we want to. So we can do nn.add dense. We'll maybe add another layer of like 4 with the activation. Well, let's do ReLU again. And yeah, and there's a lot of talks about neural networks. We don't go in that today, but I'm just doing one that I think could work well. And then we'll do our output layer. So output layer, we know it wants to be only one output node. Since it's 1 or 0, it's binary. And then we also want it to be basically binary. So if we did ReLU, it would give us a value either 0 or some greater than 0 number. But we want basically a probability. So between 0 and 1, where 1 represents its legendary and 0 represents its not legendary. So the activation function for that is softmax. or sigmoid, I think. Sigmoid is for binary. And that should be it. So now we have the architecture of it. Now we have to add the optimizer. So we do compile. So we want to do the loss, which basically tells us like loss, which is the error. We'll do binary cross entropy. I know this seems kind of random and like out of blue, and not much explanation, but basically, the loss function is basically the error and lets us back propagate. If you remember from last time, this is kind of the standard for binary classification. The optimizer, we're going to use Atom, which is um, it's probably one of the most standard ones out there. Do I import Atom though? Sorry, no, we're going to use SGD. Um, SGD. And then for metrics, for example, so we want to see like how it's working or how it's performing. Let's add accuracy. Whoop, xtrain is not defined. Oh no. Let's see what the issue is. Oh, you know what? It's because oh, sorry, I'm trying to get the data again because we restart the kernel. No module named sklearn. Alright, one second. Let me try to fix this really quick. One second, guys. I'm trying to trying to add the library to my current kernel. Conda install. Alright, it should be added now. So if I restart or stop, restart it, and then start from top to bottom, hopefully it will work. I just installed it, so I'm a little confused. Let me try again. Oh, okay, I have to add Seaborn 2, sorry. Alright, hopefully hopefully now it works. Let's stop it, restart it just in case. Alright, here we go. I think it's working now. Why you have sklearn? I just one second. Maybe it didn't install properly. Alright, well, let's try one more time. I don't think it installed properly the first time. Okay, it looks like it's working. Alright, bless. That's fine. Alright, so, okay. We're down here again. Okay, sorry about that. That was a long distraction. Um, okay, let's do Atom. I know this will work. Why is this saying? Oh, it should be metrics. Alright. Uh, it should be compiling. Okay, so yeah, we compile the model. Okay, so sorry. Any questions before we keep moving on? I know I was just kind of scatterbrained for a second. But basically what we did here is that we create a network. We have the hidden layer of 6 and 4 with input layer of 10 and an output layer of 1. And we use ReLU because that's kind of a standard. And then sigmoid because we want it to be binary output. Binary cross entropy is kind of our standard loss. Atom is our optimizer. We could also use, for example, SGD. And then accuracy is a metric that we can add on top of it, of cross entropy, to kind of let us, because cross entropy is not very useful for us because it doesn't mean much, but accuracy is easily understandable. So now we can fit it. So we can do our neural network dot fit x underscore train y underscore train, and now we can see it. Sorry. Now we can see it trained once, um, but we only did one epoch, which is basically trained once. So let's maybe add. Now let's do 20 epochs with the S, epochs with the S. Alright, so as you can see, it starts off really poorly, and then over time it slowly gets better and better. Um, and yeah. Okay, and yeah, so loss, as you can see here, it might be confusing on here, but up here it's obvious that this is the cross entropy and not our accuracy. So this is why we have the accuracy metric so easily understandable. So as you can see here, it kind of tops out at a 91% or 91.5% accuracy, which is pretty cool. And we can also evaluate it. So we can do, which is basically the same thing as our score. We can do x underscore test, y underscore test. And you can see your accuracy of 0.91. So the same thing. A little lower though, not a big deal. Where 0.4 is our binary cross entropy. So we can also change this around, right? So we don't have to do these. So one ones that have to stay constant is this, because that's our output, and then our input. So we can change this. Let's try 12 and 12. So this one seems to be performing a little bit better. Let's see. So the same output, or the same test score, but you can see training's a little higher. Let's go really low. So maybe let's try just a really small network of 3 and 3. So this one, it's about the same again. So you can see there's not much variance. We're probably gonna top out our accuracy pretty quickly. But yeah, we can also add another layers and all that kind of stuff as well, like just for fun. Let's do one more just to see. So yet again, about the same, no difference. Yeah, so you see, actually the neural network performed the worst out of all of them. Just because, just like KNN, neural networks require a lot of data with a lot of features. And since there's a low number of features, a random forest will probably work the best. That's the end of it. So I know this one seemed a little confusing at the very end, but basically the idea through this is that use all of your models. You want to basically give it a training set, and then using that training set, you want to try to find the optimal hyperparameters. And then once you have the optimal hyperparameters, you want to then use a testing set to get you your basically your final accuracy, and to make sure your model is not overfitting. This is kind of a great way to find the best model, and you don't have to use these models. You know, we talked about you can use linear regressions in that same way. You could use um, decision trees, for example, if you don't use a random forest. And yeah, and so that's kind of a basic way to do it. And we also talked about, for example, using a line plot for the best hyperparameters, or you can use something like a grid search, which you can use multiple hyperparameters at the same time. Also, for example, like the neural networks, I know it's probably the most confusing, but basically all you have to think about is that when you create a neural network, you have to determine the architecture, and then you basically want to compile it with your loss and optimizer. And that's it. If you have any questions, feel free to ask questions or look online. There's hundreds of examples of using TensorFlow and Keras um, code on how to create neural networks. And there's a lot you can learn about neural networks. It's one of the most complex, or it is the most complex type of supervised learning models out there. So I think that's it. If there's no more questions, um, that's gonna be it for me today. I'm gonna stay on for 5 more minutes. But everyone have a good day. Alright guys, I think that's it for me tonight. If you haven't signed in, please sign in the link below. Please follow us at our socials up at the top here. I think next week, I'm not sure when to do next week, but I know definitely next week we'll be doing another workshop. So, feel free to tune into that. We'll really appreciate if you guys come.